Hey, good morning, pre-calculus. This is our pre-calc test review for conics. Test is tomorrow on Tuesday. You have available on your class page this Conics X material. I'm going to be going over the sample test questions. We'll work them one at a time. I'll try to explain them. If you've got additional questions, you're going to have to go to Mr. Melson, because again, I'm out of commission today and tomorrow and probably for the next couple of weeks. Okay, let's see what we got. The first question is asking about this circle, a standard form. We have an equation given, and we have got to find its center and radius. So what we're going to do is we're going to start with the equation, x squared plus y squared. Notice the coefficients are both 1. They're both positive. That means this is a circle. 4x minus 2y minus 11 is 0. And our task is to complete the square in x and y. So I'll take the two x terms, put those together, and then leave a gap here. We're going to fill that gap in just a minute. And then I'll have the two y terms. Let me do that in a different color. So y squared minus 2y, and leave a gap there. And then the constant we're going to throw to the other side. So it was negative 11. That becomes positive 11. Now our task is to complete the square in x. Remember the process from Algebra 2. You look at the coefficient of x, which is 4. You take half of it, which is 2, and then you square that, which is going to be 4, and that's the number that goes here. So plus 4. Same thing with the coefficient of y. The coefficient here is a negative 1. We take, the coefficient is negative 2. We take half of that, which turns into a negative 1, and we square that, negative 1 squared, which is 1, and that's what adds here. Okay, so we've completed the square in both x and y. However, the equation I have here is wrong because I've changed the left side by plus 4. I have to do exactly the same thing to the right side. And I've changed the left side by plus 1, so I have to do the same thing to the right side. Okay, so yeah, those pieces have got to be included in the problem. Okay, now once we've done that, we can go ahead and rewrite this as the square of a binomial so that we can actually see the center and radius. So this becomes x plus 2 quantity squared, and this becomes y minus 1 quantity squared, and this is what it is. It happens to be, what's that, 15 plus 1 is 16. Okay, so the center is going to be given by these numbers. Now remember, the graphing form was here. It's x minus h. So the center is going to be minus 2. And again, y minus k. But this already is a minus, so minus a minus would be plus 1. The radius is on the right side. Well, actually, the radius squared is on the right side. So 16 is the radius squared. The radius is 4. Now, in addition to doing that, the problem did say sketch the circle, so we have to do that. So we're going to go to the grid. We find negative 2, 1, which is right here. And then we go 4 units in all directions. If we had a compass, we could actually spin it around, but I would just count boxes. 1, 2, 3, 4 up here. 1, 2, 3, 4 over here. 1, 2, 3, 4 over here. And 1, 2, 3, 4 over here. So there's 4 units in every direction. It looks like this grid is sort of distorted. This is supposed to be a circle. It almost looks like an ellipse here, but yeah, the grid is a little bit off. That would be a sketch of our circle. Okay. Notice, by the way, that there are x and y intercepts. The x-intercept here is pretty clearly 2, and the x-intercept here is a little bit less clear. Well, actually, I say it's clearly 2. It's probably not 2. This point right here is 2, 1. This point right here is going to be some number a little bit less than 2, and I don't know what this one is. This is some number between let's see, -5 and -6, so approximately -5.5-ish, right? And the same thing with the y-coordinates. You could, if asked, find these y-coordinates. That might be a quick bonus question. You should know how to find x and y coordinates for any conic section. Okay, second question. Second question is talking about a parabola. It does say a parabola opening to the right. So opening to the right means looking like this, right? And we have the equation. Actually, we don't have the equation. That's one of the things we're supposed to come up with. So let's go ahead and plot what we do know. We do know there's a vertex at 0, 2. So this is where the parabola turns around. Now at this stage, the best we can do is we know the parabola is doing something like that, but we don't know exactly how it bends yet. But we do know that's the vertex. Okay. What else do we know? There's a directrix at x is equal to -3. So here's the line, x is equal to -3. X is equal to -3. And that's given as the directrix. Now you might want to remember the river and well problem. Remember the river and well. The focus point, the well, was 6 units away. This is going to be our focus. And sure enough, the vertex right here is halfway between the river and the well. And this is very similar to the problem that you did back when we did that little exercise. If we wanted some additional points on the parabola, we know that there was 1, 6 up, 1, 2, 3, 4, 5, 6, and 1, 6 down, 1, 2, 3, 4, 5, 6. So this is a much more accurate sketch of our parabola going through that point and then bending down and going through that point right there. Okay, so there's the sketch. So we've got that sketch of the parabola. The focus point we found. Remember the distance from the vertex to the directrix. This was called P. It's the same as this. This is P. Okay, so in the ellipses and hyperbolas, we were calling that C for focus. But for parabolas, for some reason, we use the letter P instead of C. Okay, so the focus point, I guess we should go ahead and write the ordered pair. We can count, let's see, 1, 2, 3, 2, 3, 2. The eccentricity, remember by definition, is 1. And again, you have available, let's see where I can find it. Hang on. You have available everything you wanted to know about conic sections. So certainly I would print this out and look at it. And the very last fact of parabolas here, number 6, the eccentricity of a parabola is defined to be 1. So in this problem, when it said, what is the eccentricity, you just write 1 and you don't have to do any calculations. The equation's a little bit more interesting. So let's see, we were given this structure, x minus h is 1 over 4p times y minus k squared. That's parabola opening to the right that was given in the problem. And we have the vertex point, that's our hk. So this vertex is hk. You can think of it as the center for a circle or an ellipse or a hyperbola, the hk. And so those numbers fit in here. So we have x minus 0. Or maybe we should go ahead and write down this vertex point is the ordered pair 0, 2. And again, they gave that to us, so that's not anything that we had to worry about. So we got x minus 0. We've got 1 over 4. Now again, the p is the distance from the focus to the vertex or the vertex to the directrix. In either case, it's equal to 3. So we can write that. And then y minus 2 quantity squared. Okay, so there's the equation for the parabola. If you wanted to clean it up, you could. I would be very happy with that. X is 1/12, y minus 2 squared. Or if you want to multiply by 12, 12x is y minus 2 squared. And just sort of as a reality check, let's take a point that we said was on the parabola. Remember, we said that this point right here, 6 down, 1, 2, 3, 4, 5, 6. This point was on the parabola. That would be the ordered pair 3, and -4, just to make sure that we're not messing things up. Let's make sure those coordinates fit into the equation that we've come up with. So if we put in 3 for x, this becomes 12 times 3, and we put 4 in for, -4 in for y, so that's -4 minus 2 squared. This should be a true statement, and sure enough it is. This is 36, and this is -6 squared, which is 36. Okay, so at least our equation holds for that one point, and I think if you tried, the other point up here, it would work, right? If you tried the vertex, it would work. And in fact, there's an infinite number of points on this parabola. Okay, question number 3. Number 3 is a ellipse, and our task is to find all of this stuff, the last thing being the equation of the ellipse. And we're not given the center, nor the length of the axis, nor the eccentricity. Those are things we're supposed to find. We are, however, given the 2 vertices, -5, 0, and 7, 0. So we have that. And the 2 focus points were also given as -3, 0. I'll do green for focus, and 5, 0. Okay, so these are our 2 focus points. Now, in general, we know that the vertices are at the ends of the ellipse. So the ellipse is looking something like this, which is consistent with what the problem told us, a horizontal major axis. Now, we still have to get the exact graph that does say, sketch the ellipse, and this sketch isn't going to fly. It has to be much more accurate than that. So let's see if we can do some more work here. The center of the ellipse is the point that's right smack dab in between the 2 vertices. So if you look at the length of the major axis, this is 12. 12 boxes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the center would be 6 away from the ends, 1, 2, 3, 4, 5. Here's the center of our ellipse, and we could write that down, 1, 0. And we've got the major axis. Now the minor axis is the vertical dimension, but we don't have that information yet, so we're going to have to hold that in abeyance. The eccentricity, by definition, is C over A, but again, we don't have, maybe we do. C, remember, was the focal distance. And because we know the center, and because we were given one of the 2 focus points, in fact, we were given both focus points, this is C. So that's 1, 2, 3, 4. So C is 4. C is 4. So maybe we can actually get the eccentricity right now. It's 4 divided by A, and A is the length of the semi-major axis, right? And we sort of can count that 1, 2, 3, 4, 5, 6. Okay, so 4/6 or 2/3 is the eccentricity. So we've got that. Now the last thing we need to do is we need to figure out what this B number is. Okay, so we've got, here's our standard form. We've got the center, so that gives us HK. We've got the semi-major axis length, which we said was 6, so 6 squared is 36. What we don't have is this B number. So we have to get that. That's going to be the length of the semi-minor axis. And how do we do that? There is a relationship, remember, for ellipses between A, B, and C. C squared is A squared minus B squared. And for our problem, we were told that the focal length, or we figured out that the focal length is 4, so that's 16. And we've got A squared, remember this is A, so that's 6. A squared is 36, and then minus B squared. So a little bit of subtraction, we get B squared is 20. Okay, so let me go straight to the equation of the ellipse. Let me take my eccentricity away here so I have some room. The equation of the ellipse, we've got all the pertinent information. We know the center is 1, 0, so we can put that in for H and K. X minus 1 squared, Y minus 0 squared. The A squared we figured was 36, and now we have the B squared we figured was 20. Okay, so the length of the minor axis. Well, 20, what's 20? Let's see, that's B squared. This is B squared, so B is going to have to be the square root of 20, which will sort of have to approximate as, say, 4.5. 4.5. That's the approximate length of the semi-minor axis. And so when I draw my picture, I'm going to go from the center and go 4.5 units approximately. 1, 2, 3, 4, and a little bit. Okay, so this will be the top of the ellipse, and the same thing coming down. 1, 2, 3, 4, and a smidgen. Okay, so now I can draw my ellipse going through those points. If I were looking for the sketch and to grade it, I would be looking for this point right here, not to be up at 5, but somewhere between 4 and 5, and the same thing down here. The bottom of the football is not going to be at -5, but between -4 and -5. And this distance, even though we didn't ask for it, is the square root of 20. Okay, so there's a good sketch. Length of the minor axis, 2 square roots of 20. And yeah, you can clean that up if you like. Don't have to if you wanted to simplify it. So what's that? 4 square roots of 5. 4 square roots of 5, because 20 is 4 times 5, right? So 4 square roots of 5. Okay, that's problem number 3. Let's go to problem number 4. Standard form of a hyperbola with a horizontal transverse axis. They give you that. Here's an equation. It graphs as a hyperbola. Sketch the hyperbola, and then identify center, length, etc. Okay, so all of these things we're supposed to do. We're given a grid. The picture has to fit in the grid. By the way, if you get numbers and it doesn't fit in the supplied grid, you're probably doing it wrong. Okay, so let's see what we've got. Well, look, they actually told us the center right off the bat. We know the center is at H and K, and they gave us those numbers, 2 and -3. So 2 and -3, here's the center of our hyperbola. Now, like the ellipse, the dimensions in the x and y direction are given by the a squared and the b squared. So a squared is the 1. Remember, that's from the positive term. And the b squared is 9, and that's the one that comes from the negative term. Okay, so a squared, b squared. And so let's go ahead and sort of sketch our little box. In the x direction, we'll go 1 unit. So here's a side of the box. 1 unit to the right, 1 unit to the left. And in the y direction, we're going, right, 3 units. So 3 units up, which is right here, and 3 units down. Okay, so here's my box that the hyperbola is going to be built around. It does say transverse axis. Remember, transverse is the axis that connects the 2 branches. So we're looking at a picture like this. This is the horizontal transverse axis. They want to know how long that is. So by looking at the box, we can pretty much tell that that's going to be 2 units long, going from there to there. Okay, so the length of the transverse axis is 2. Let's go and put all these things down that we know. This was 2, -3. Length of the conjugate axis, that's the one going this way that doesn't connect the 2 branches. And so that's obviously 6, just counting boxes. Coordinates of the 2 vertex points. The vertex points are where the hyperbola touches the box. So we have those. And we can write those down. What do we've got? We've got 3, -3, and 1, -3. Okay, so those are our 2 vertex points. Foci, we're going to have to calculate the focal distance. Asymptotes. Let me go ahead and draw in the asymptotes so that we can actually sketch this. Okay, so the asymptotes are the diagonals of the box. So it's going like this. So this is one diagonal. This is the other diagonal. Okay, and then there's a diagonal going this way. And going this way. Okay, and our hyperbola is now kissing the box. These are the 2 vertex points again, and it approaches that asymptote. So approaches the diagonal, kisses the box, and then goes out that direction. Okay, so one of the things we were supposed to do was sketch the hyperbola. I've got a fairly accurate sketch here. We need the equations of the 2 asymptotes. That works really well as long as you know the point slope form of a line. y minus y1, m times x minus x1. The point that I'm going to be using is the center, because that's certainly on both of these asymptotes, and that's the point 2, -3. So I'll put that information in, x minus 2, and y, now minus a minus 3 is y plus 3. We do have to figure out the slope for these guys, but that's pretty easy to do if you just look at the dimensions of the box. If you're going from the center point to this diagonal corner, you're going up 3 and over 1. So the slope is 3. But for the other asymptote, you would be going down 3 and over 1. So the slope could be -3. So here we have two lines. The plus or minus 3 would be the slopes. They both go through the center of the box. So that's a good way to write the equations of the asymptotes. Okay, we do have to get the focus points, and that will give us the eccentricity. Eccentricity is, again, c over a by definition, and the equation for the focal distance of a hyperbola, c squared, is a squared plus b squared. So for our problem, c squared is 1 plus 9, c squared is 10, and c is the square root of 10, which is about 3.5. It's probably closer to 3 than 4, but let's say 3.5, some number between 3.5. And so that will be our focus distance. And so let's go 3.5 units away from the center now. So 1, 2, 3.5. So this is one focus point. And from the center, 1, 2, 3.5. There's our other focus point. Once we have the c, we can get to the eccentricity. The eccentricity would be the square root of 10. And again, use the exact value. Don't use 3.5. Divided by a, and we said a was 1. Okay, so the eccentricity is the square root of 10. What do we need? We need the coordinates of the two focus points. So that's the last thing. And I guess if we look at these 2 points, it's pretty clear that the y-coordinate for both of these, the y-coordinate is down here at -3. Because all, the two focus points and the center, they all have a y-coordinate of -3. So we just have to figure the x-coordinate. And the way I'm going to do that, I'm going to start with the x-coordinate of the center. So here's my center point. And that x-coordinate was 2. And then to that, I had to go the square root of 10 to the right. So 2 plus the square root of 10. And for the other one, we're at 2. But now we're going 2 square roots of 10 to the left. So that's minus the square root of 10. So there's your x, there's your x, and your y is -3. Okay, so that's a sort of a difficult problem. You'll see another one of these types coming up in just a little bit. Okay, next question. Oh, this looks like a quickie. We should be able to, just by looking at the equations, identify whether these are lines, parabolas, ellipses, circles, or hyperbolas. Please work your problems, not your neighbors. There's going to be 2 or 3 forms of the test. I'm going to jumble these up. So just because the person next to you writes LPECH, that doesn't mean you're going to write LPECH. It may be in a different order. Okay, so let's go after the line first. The line is the trivial one. That's the one that has no square term. That's a line. Parabolas are probably the next easiest. The parabolas are the ones that have only one square term, right? Like y is equal to x squared, or x is equal to y squared. So one square term will be a parabola. This one's a parabola. Not that one, not that one. This one is a parabola. Okay, one square term. Now, for 2 square terms, we have ellipses, circles, and hyperbolas. And again, it's probably not a bad idea to go back to this sheet that you have. Everything you wanted to know about conic sections. If you look at circles, right? Circles. I don't think I can write on this. No. If you look at circles, the general form for equations of a circle, ax squared plus by squared cx dy e. X and y are both to the second power. A and B are the same number, right? If A and B are the same sign, but different numbers, you get an ellipse. And if A and B have different signs, then you get a hyperbola. So going back to this, probably the first thing we should do is move everything to the left so we have equals 0. So let's see, for this third one right here, I have 8x squared plus 8y squared is equal to 10. For this one here, I already have everything on one side. X squared plus 8y squared is equal to 10. And for this one, if we move everything to one side, we have x squared minus 8y squared is equal to minus 10. Okay? Now, again, just by looking at the coefficients, you can identify these. For the first one, the coefficients are positive and equal. That's a circle. For the second one, the coefficients are 1, right? 1 here, and 8. They're both positive, but they're unequal, so that's the ellipse. And for the last one, the coefficients could be equal, but they're in fact different signs. One's a positive 1, one's a negative 8, so that's our hyperbola. Okay, so pretty quick and easy. You don't have to graph any of these. You just look at the equation, and you can tell what they are. Okay, oops, let's see. Let's go number 6. Conic with a horizontal directrix below the pole has a polar form. Determine whether the equation is a parabola, ellipse, or a hyperbola. Find the eccentricity, and as a bonus, if you can find the equation of the directrix, that would be great. Okay, so let's see what we know. We have a, I don't have a polar grid here. I'll tell you what, let me pause this briefly and bring in a polar grid so I can actually do this. Sorry, don't want that. Where's my recording icon? There it is. Okay, so let me pause this just for a sec. Okay, back again. I've pasted in a polar grid to make this a little bit easier to play with. And we're told again in the problem, we have a horizontal directrix below the pole. So imagine the directrix down here somewhere, horizontal below the pole. That's what's given in the problem. And we're given, it has to look like this. And we're given this equation. So if we start to match up things, R is E times D. By the way, D is the distance to the directrix. 1 minus E sine theta. And we have R is equal to 3. And then 1 minus 2 sine theta. It's pretty clear, I think, that the eccentricity has to be the number 2. Everything else is good. This is a 1. This is this. This is a 1, this is this. Okay, so the eccentricity is 2. Now, where do we go from there? Once we have the eccentricity is equal to 2, we should know what kind of conic it is. Remember, if the eccentricity is 1, that's by definition a parabola. If the eccentricity is less than 1, that's an ellipse. Greater than 1, like 2, we have a hyperbola. Okay, so this is a hyperbola. And we have the eccentricity is 2. Now, the distance to the directrix. This number up here was given as E times D. So let me just write that. 3 is the same as E times D, but we know that the eccentricity is 2. So 3 is equal to 2 times D. 2 times D. And so the distance to the directrix is going to be 3 halves. 3 halves. Okay, so let's see. What that means is our directrix now is going to be 1.5 units below. So I'm going to draw a horizontal line right here. And the equation of that horizontal line would be minus 1.5, or if you want, minus 3 halves. I know it's horizontal because they told it to me. I also know it's below the pole because they told me that. Okay. And this is our focus point. It might be interesting to go ahead and try graphing this on your calculator. You don't have to, although we will in just a second. You'll note that the hyperbola fits in like this. Okay. So, and the vertex of the hyperbola, now in fact we can tell exactly where it's going to be. The vertex of the hyperbola is going to have a ratio. Let's see. There's the focus point, And so the vertex, the ratio is going to be 2 to 1. So I think we're going to go right through that point right there. And that point being the XY pair, 0, -1. If we're in R theta, there's lots of R thetas you can put there. So let's go ahead and throw this on the calculator just to see. All of this work I've done without a calculator, but you can certainly do this if you want. I don't know that you need to, but I'm just going to try to confirm my sketch there. So let's see, I would have to be in polar mode, and the equation that was given was 3 divided by 1 minus 2 sine theta. Okay, and here's the graph in the standard window. Okay, now notice for this particular calculator, it does throw in the asymptotes, which some calculators may or may not do. Let me zoom in a little bit. Okay, so here's the hyperbola. I'm going to trace along and see if I can find a point where my cursor might be. Okay, here we go. We're coming in, and sure enough, it goes through the point x is 0 and y is -1. Okay, so that's sort of a sketch of our hyperbola. There's obviously another branch down here somewhere, and I wasn't asked to sketch that. In fact, I don't have to sketch anything to get credit on this. Okay, next one. Hopefully this will go a little bit more quickly. Again, we have our, let's see, vertical directrix now to the left of the pole. Let me go back and copy this and paste it over here. Okay, so here's my polar grid. It tells us we have a vertical directrix to the left of the pole, so it's somewhere over here. And our task is to determine whether this is a parabola, an ellipse, or a hyperbola. And once again, we just sort of made this up with this expression. And it's pretty clear that the eccentricity, this number here, has to be 1. Eccentricity 1, this is a parabola. Don't have to do anything beyond that. So eccentricity is equal to 1, sort of a gift. And then the equation of the directrix, okay, so the number on top here, this in the formula was E times D. That's supposed to be 6. We know the eccentricity is 1, so the distance to the directrix is going to be 6. So we're going to go 6 units and draw our directrix. 1, 2, 3, 4, 5. I'm right out of the picture over here. So this is our vertical directrix to the left of the pole, 6 units away. This is 6 units away. And the equation of this would be x is equal to -6. Okay. Again, we don't need our calculator, but let's go ahead and just verify that this really is a parabola. So we have 6 divided by 1, whoops, parentheses, Joe, 1 minus cosine of theta. Zoom 6. Okay, so there's our parabola. In fact, you see the vertex going right here, 1, 2, 3, right at this point, which is like at negative, XY world, this would be -3, 0. So there's our parabola, and sure enough, that's what it looks like on the calculator. Okay. Equation for the directrix, we did that. That was x is equal to -6. Okay, number 8. Hopefully after seeing these three, these problems do go pretty quickly. We're going to have to figure out the eccentricity, and that will tell us whether it's a parabola, an ellipse, or a hyperbola. You might suspect, since we've already had a hyperbola and a parabola, this is going to be the ellipse. But let's go ahead and figure out why. In order to use this equation, the number right there has to be a 1, and we have a 2 in that slot. So we're going to have to do a little bit. Let's divide the top by 2 and the bottom by 2. Okay, so I basically multiplied this equation, or the right side of this equation, I multiplied it by 1 of the form 1/2 over 1/2, right? You can certainly do that. And I ended up with this variation, And why do I want that? Because now the number in front of the trig function is in fact a 1, and I can read off my eccentricity very easily. I've got 3 on top. I have 1 plus 1/2 cosine, and because this is smaller than 1, that gives me my ellipse. Okay, so the eccentricity is 1/2. And let's get the equation for the directrix. Once again, we'll look at our grid here. Now the problem does tell us this is a vertical directrix to the right of the pole. So we're somewhere over here. And the question is, what's the equation? This distance is d. And in the problem, it was told that the numerator is e times d. So here we are. This is e times d. 3 is e times d. But we've already calculated that e is 1/2. So that means d has got to be 6, right? To be 6. So when I'm drawing my vertical directrix to the right of the pole, I'm going to go 6 units. 1, 2, 3, 4, 5, 6, and I'm over here. Okay, so this is x is equal to 6 would be the equation of the directrix. And again, that's a bonus thing, so you don't have to do that and still get an A+. You'll be okay. Quick verification. If we look at the equation, we have 6 divided by 2 plus cosine theta. Here we are. Sure enough, it is an ellipse. The focus is the pole. If we actually looked at the vertex point, you'd notice the vertex point is going right through this 2 point here. Oops, sorry. Going through this 2 point right here, and the ellipse is looking like that. Okay. Again, you didn't have to draw this. Okay, next question. Now, this is an applied problem. The standard form of a hyperbola with a horizontal transverse axis, cooling tower with hyperbolic cross sections. Number 10 is another applied problem, a solar collector for heating water. You might want to look in your textbook. This is a screenshot from page 642. And this has a satellite dish, which is like the solar collector problem. And it has the solution. You might want to look at 642. Here's an ellipse applied problem, 653, example 9. You might want to look at that. Here's a problem out of the hyperbola section, 669. It's an exercise set, and it's got nuclear power plant, hyperboloid, and it's asking questions there. So you do have examples and exercises that have applied problems. Expect a couple of applied problems. One might be an ellipse, the other might be a parabola. You might have an ellipse and a hyperbola. You might have a hyperbola and a parabola. Okay, so for this particular practice test, we've got this. Let's see what's going on. A cooling tower, the hyperbolic cross-section. The transverse axis has length of 50 meters. Now, here's the center. Here's the center. And so this is 25, and this is 25. That's the transverse axis, right? Notice that we do have this horizontal transverse axis. A is the distance there. That's the positive term. And by looking at the picture, we know that A is 25. Okay, so right now we have x squared over 25 squared. We're going to have to figure out the B number, right? B squared. And we can do that by looking at the equations of the asymptotes. So we know that the slope is 4. So if this is the center of the box, one of the corners is right here. So even though we don't have the box drawn, we do know that the box looks something like this. And it's going to be going up here somewhere up to the top. But yeah, this asymptote has a slope of 4 going through there. This asymptote has a slope of -4 going through there, and obviously continuing up, but we don't have the top of the box shown. We just have the bottom of it. And so the B number is going to be this distance. Now, each grid is 25 meters, so we're not going 4. This is 100. So this would be 100 squared down here. Okay, so that would be that one. Equation of the hyperbola, got it done. Next guy is a solar collector for heating water, is constructed with a sheet of stainless steel that's formed in the shape of a parabola. The water will flow through a pipe located at the focus. At what distance is the pipe from the vertex? So we're looking for the P number. If we try to redraw this, there's a hint on how you might consider this. You should consider an upward opening parabola, the vertex at the origin, and one point on the parabola at 3, 1. Okay, so our parabola is looking like this, upward opening parabola, and the question is, where do you put the focus? So there's a focus up here somewhere, and we're trying to figure out this distance P. Okay? Well, for parabolas opening up, they're like y equals x squared. That's our general opening up parabola. If we get a little bit more particular, we can throw in the h and the k, y minus k, 1 over 4p times x minus h squared. So that's our parabola opening up. For this one, we're considering the vertex to be at the origin, 0, 0. So both the k number and the h number are 0. So we have y is 1 over 4p times x squared. And our task is to figure out p. How far is the focus away from the vertex? Well, what do we have? We have a point that's actually given. And you might want to go to the problem and just note that the way the solar collector is constructed, it's 6 meters from tip to tip, right? And the depth of the solar collector, this sort of distance here, is 1 meter. So yes, this is 1 meter right here, from here to here. That's 1 meter. And because the entire thing is 6, half of that is 3. So that's how we got that 0.31. And it has to fit on the parabola. So let's go ahead and put 3,1 into the equation, and we should be able to figure out what p is. So y is 1, and x is 3. And so we just solve this for p. Pretty straightforward, I hope. So we have 4p is equal to 9. P is 9/4. Okay, so how far away is the distance, the pipe from the vertex? The answer is 9/4. Make sure you have the correct units because we're talking meters. I would say this P number is 9/4 meters if you want 2.25 meters. Okay, so graphically, if we were trying to do an accurate graphical representation, this is 1, this is 2, this is 3. So our focus point is right about there. Okay, there's focus and there's vertex. Well, I hope this helped. Good luck tomorrow. Problems very similar to these, similar difficulty, similar length. And then on Wednesday, we start the last section of the course on limits. Okay. Signing out.